the need for spectrum and how to get it. And at seminars, I will switch to English because, let's say, there are some English people in the audience that otherwise don't understand what we are saying. So my excuses for that. I'll continue in English as speakers will. So the topic is the need for spectrum. And let's take a look at this picture that illustrates this, which it comes from Ericsson in 2022 and shows the increase in exabytes, number of a big exponent. I forgot what it is exactly. Yeah. So, and that all needs to be transported over the airwaves, and for that we require spectrum, and there will not be enough of it. The spectrum situation landscape as it is now, as for example in the United States, you see there from 300 gigahertz, how it is divided up. A lot of it is spectrum that is committed, that is licensed, some of it is not. So one has to, in that big spectrum, one has to accommodate the, let's say, the amount of resources that are needed to satisfy that big demand for spectrum. How to get more spectrum? Basically, there are two ways. One is to use unused spectrum, new spectrum, for instance, millimeter wave, terahertz spectrum, and optical is, of course, something obvious. There is a huge amount of spectrum available, but it has some drawbacks. The coverage is low because of propagation losses. And for that reason, it's only or mainly suitable for local usage and spatial reuse. That's a good thing through dense picocell and things like beamforming. So that's one way. But if we want good coverage, then we will have to go, let's say, explore what are the possibilities in the spectrum that is used now. So better usage of licensed and unlicensed band, and that's what dynamic spectrum sharing wants to achieve. The present situation and the opportunities are as follows. There are many licensed frequencies bands that are little used in time or space. So, for instance, bands allocated to radars, military purposes, satellites, etc. And on the good side, the demands for spectrum are often, let's say, limited in time and space. For instance, for big events. So if we have like at the time a Rolling Stones concert on the Malieveld, then you need it only for that time. And also, if we look on a microscopic time scale to the usage of the spectrum, licensed as well as unlicensed, the transmission times at the time scale of transmission times or slots, a lot of spectrum is also not used. So those are the areas where spectrum could be shared if we had the right procedures, methods, techniques, and policies. So there is need for something like spectrum access control across all spectrum users, operators, private networks, radars, broadcasters, satellites, airplanes, all these users. Something like medium access control for a single network, which is about sharing a medium within a single network. In this seminar, we have two perspectives. One is from research, and that will be taken care of by Spilios Giannoulis of University of Kent and IMEC, and spectrum, the perspective of the regulator, and that will be done by Frank Bodewes of Dutch Digital Infrastructure Authority, used to be called Agentschap Telecom. So well known. So I propose, just a second. start with the first speaker, Spilios. And I'll tell you a little bit about Spilios while he gets his setup working properly here. Spilios received a degree in electrical and computer engineering and PhD. Oh, sorry, I have to speak here. Yeah, exactly. Shouldn't walk away from the microphone. Got a PhD in computer engineering. He has been a researcher involved in several EU and national R&D projects in Greece, University of Patras. And then he's currently a senior researcher in IMEC in Belgium and involved in several EU projects in the area of reconfigurable and adaptive wireless networks. And he has served as a technical leader in the Wishful project, which is about this topic. And he also, and that's noteworthy, definitely this leader of the Scatter team that took part in the DARPA Second Spectrum Collaboration Challenge. And that's something organized by DARPA, and they were able to get a grant of $1.5 million, which is not negligible, I would think. He also led an ESA, European Space Agency project, and of course, member of IEEE, and is interested in a broad range of topics, I would say, all related to networking and wireless stuff. So I'll leave it at that. Has written many publications, so if you go on the web, you can also stuff of Spilios.
Thank you very much. Thank you very much. As already mentioned, I'm Spilios Giannoulis. I'm coming from University of Ghent and IMEC. We always wear a double hat. And I'm going to give you a small overview of the status of dynamic spectrum sharing on the research domain, especially focused on what is happening right now in the EU. So that's the outline of my talk today. I'm not going to go now into details, but just to figure out.
Spilios, sorry that I interrupt. You are not sharing your presentation.
I am not. Okay, let me see.
Yeah, that's it.
Yes, that's okay. Yeah.
Okay, perfect. So I'm going to talk about a bit the status today, what is happening today, how do we share spectrum today, both on the terrestrial domain, but also on the satellite domain, because I think both of them are very relative to each other, and we need to find a way to make them work together. Why do we think now is the time to try to push forward for dynamic spectrum sharing? How can we enable dynamic spectrum sharing? I'm going to say DSS from now on, so I don't say all the time dynamic spectrum sharing is becoming a bit too much. What are the gains, the possible gains and the challenges of DSS? And then see what's happening right now in the EU, and what have we done so far in IMEC towards DSS. And then I'm going to finish with a takeaway message, which I think is very relevant to the status of DSS today in Europe. So just a very quick overview of how we used to use spectrum in the past and how this the range of applications is growing. This figure is quite old. It finished at 2000. Now we're at 2023. So you can imagine that the 40 applications, more or less, that we had at that time. Yes, indeed. That the 40, let me also make that a laser pointer. Okay. So that the 40 applications that we had at that time now have become like 100, 150 applications, and it's growing exponentially. So at this specific time, we are trying to pass so many data through the wireless spectrum, and this need will only grow in the future. And that's a very clear indication that we really need to find a way to automate this kind of procedure and not follow with the fixed approach that we have today. But I'm going to come into more detail on that later down the road. So that already has been shown by Ignas. That's a very nice slide. Everybody uses it when they want to talk about dynamic spectrum sharing. That's the fixed allocation status of spectrum in the United States. This graph shows, first of all, the complexity, how many technologies right now want to share spectrum, want to use spectrum, the static approach that we are following right now, and also how many parts of the spectrum are already not being used, although they could be used in some applications. So we wireless engineers know more or less that right now in the entirety of the world, the 99.9% of spectrum that is being used for communications is in the sub 7 gigahertz. Only satellites go beyond that, and only now some applications are rising, like 5G is trying to go into the 10 to 20 gigahertz range. All the rest is not used right now, either because the technology is not there yet, like terahertz. We don't have terahertz transceivers right now, or because the actual physical capabilities of that specific frequency range is not good for applications that we want to use it in. For instance, 60 gigahertz cannot penetrate walls, cannot penetrate even a single leaf of a tree. So the moment you have something obstructing the line of sight between transmitter and receiver, you have a huge SNR loss. Let's not say completely lost, but you lose like 10, 15 dB. And that's a very big problem for wireless communications. So that being said, I will try to start with an analogy. What is DSS, by giving an example of how we use roads today and how we actually would use roads if we would follow the approach of static allocation that we have today in wireless communications. So the today approach that we're using in wireless communications is more or less what we see in the left figure. So we have specific users, let's say the white cars, that have bought a specific part of the road, and they are the only ones allowed to use that part of the road. If they have too much traffic, they will have to queue the cars that cannot fit in the road until there is space in the road to use it. If they don't have traffic, that part of the road will remain free. Nobody will use it because nobody else is allowed to go there. They have bought that lane. On the other hand, if you have a user like the yellow small cars that didn't have money to pay for the road, and they didn't even have the ability to buy a small part of a lane, but they only have to buy the entire lane, then that specific type of car will never use the roads because they cannot go through the barrier of buying an entire lane of the road. And that says a lot about the economic aspect of how we are using spectrum today, we are selling spectrum today. On the other hand, what we aim for the future is the figure on the right, where we have now all the cars that were waiting in queue because they didn't have either enough space in their bought lanes or they didn't have a lane at all. They are now able to fit in the road. It's the same road, nothing has changed. We didn't build more roads. It's the same road, exactly the same capacity, let's say, of the road. But now because we have more flexible approaches into sharing the road, into buying the road, into maybe leasing the road per use, we are able to have all the traffic being served. And also we have even some more gaps that if more customers, let's say, come into play and they want to use the road, that's possible. So that's where we want to aim also for the wireless spectrum. We want to be able for everyone to use the spectrum, pay for the spectrum that they use, but not have that huge paywall of a few hundred millions if they want to buy a specific lane or a specific frequency, as it happens today in the frequency domain. And I think that's a very good analogy, and I will come back to that as I will explain more later down the road. So keep the time. Okay. So what is dynamic spectrum sharing? Now going a bit more into technical details. Again, that's the isolated approach that we use today, the fixed approach, where every technology, LTE, Wi-Fi, 5G, DVB, and so on and so forth, they have their own frequency ranges. Some of them may be used by others, like Wi-Fi does with the ISM bands, but more or less, you have like fixed allocations of frequency ranges per technology. And what we want to avoid is the waste of frequency, the waste of spectrum that happens when you're actually doing that. As I explained in the road analogy, if one technology in one specific place and one specific time is not being used, that means that that part of the spectrum is being wasted. If somebody buys in the Netherlands a specific frequency and they only use it in the big cities and not in the rural areas, and nobody else has the right to reuse that spectrum in the rural areas, then that frequency capacity, that spectrum capacity is being lost. Nobody has the ability to use it and nobody can buy it. So what we want to avoid is this kind of waste of spectrum by moving forward into something like this, an autonomous and collaborative way of sharing spectrum. We have machines. The machines have the capacity to think nowadays. We can have very intelligent algorithms of exchanging information between machines, and collaborating between them. Why try to solve a problem statically by statically allocating spectrum today as we do it, and not allow the machines to solve it where it needs to be solved, and that is in the local collision domain. That's the main issue that we have to figure out today. How are we solving this problem? This problem can be solved only where the receiver exists, only where you want to make a reception. Only the receiver knows its local collision domain, nobody else. No model can tell you that. It can approximate it, but it will never be able to tell you exactly the base ground truth. So we're always saying, follow the receiver, allow the receiver to tell you what's happening in its collision domain, and then make decisions on how to use the spectrum to avoid interference. By having multiple systems running in the same space, if some global, let's say, entity or central entity wants to see what's going on in the operation of those technologies, he will see something like this. So let's say here I have like 7 technologies, and they are sharing the spectrum in a more or less chaotic way. But this figure only shows frequency and time. Space is not there. If I wanted to add space, I would need to add multiple layers behind that figure so we can also see space. And how do you define space? How many space axes do you need? Is it per 10 meters, per 100 meters, per 1,000 meters? What is your step? How are you going to build a database for that? If you go to a single system looks like this. Now I just chose TAF2 technology from the global view, and then I went to the single system view. Still, a single system can have multiple transmitters and receivers, and they are not always in the same collision domain. So even that figure here is lying. It says that the entire technology TAF2 is using all of this spectrum at all places that is operating at all times in this specific frequency and time domain. But that's, again, it's not true. For a single receiver, you need to see what's happening in his own collision domain, which is exactly that. So a single receiver of TAF2 technology will probably sense only a sub portion of the full system operation, because it has a specific range, tens of meters, hundreds of meters, even a few kilometers. Still, it will not see the entire collision domain, like, say, the entirety of the Netherlands. That means only he will be able to know exactly which parts of the spectrum are being used by his own technology, TAF2 technology, but further down the road, also see external unknown technologies, because you can still sense energy. You don't need to be able to demodulate the packets. So a single receiver will be able to see what's going on from his own system to avoid internal interference, as we call it. So interference coming from your own system, from your own nodes, but also external interference the moment you identify that this specific receiver has some other technologies in his collision domain that are transmitting in some other manner. All you have to do is avoid it. You don't need to understand it. Just see the energy that is there. If you can figure out a pattern, fine, even better, and then be able to proactively arrange so you never interfere with those other technologies. This kind of approach is what we call single RX view, and we argue that interference is best perceived, is only perceived at the receiver. That's the ground truth, that any model you will try to build to approximate that, it will be exactly that, just an approximation. So why do we need approximations when we can have the ground truth where we want it, where we need it? We need it on the receiver. The receiver has to be able to tell to the transmitters that are transmitting towards him, hey, I have issues here, 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 and here. Don't transmit in these frequency time slices. They are used by others. I don't know who, I don't care, as long as you don't transmit there. And in his own system, I already have set up links with these 3, 4, 5, 10 other nodes in these specific frequency time slices. So you're free to connect with me in any other slice apart from those. Interference problem solved, external interference problem solved, frequency reuse maximum. Because if you see the single system view and the single RX view, for instance, this part here, this slice here from the single system view is not being seen and is not being used by that specific receiver. So he can reuse it. And then the reuse vector of this slice is 2. If multiple nodes do the same, then you can have the reuse factor of a specific slice to come 5, 10, 20, 30. That's how you multiply frequency spectrum. That's how you multiply spectrum without actually doing anything magic. You're just making sure you can do spatial reuse in every receiver that is not seeing specific parts of the transmissions that are happening outside of his collision domain. And that's exactly what DSS comes to do, to take advantage of all the time, space, and frequency separation that happens either by chance or by design in the time, frequency, space space. That's what we want to aim for. And the only way we can do that, if we allow the machines to have this knowledge that they can very easily have, each receiver can very easily have this view, and then based on that view, collaborate, communicate with their counterparts, and make sure they set up links to avoid external and internal interference. I think that's the way we need to see things. It's a very generic approach. It will not work just for LTE or just for Wi-Fi or just for anything else. It will work for any wireless technology that we have today and that will possibly come in the future. I have no problem. If you have a question now, I can surely take it. Fairness. So yes, the
Maybe,
question is,
sorry, could you repeat the question because
yes,
for
I
the
will.
people online it's not
I will.
possible.
So the question is, how do we ensure fairness if in such a system where you have its, let's say, technology being able to take and use specific parts of the spectrum? So that's where regulators will come into play. And I think also the payment will come into play. We need to change the way we use spectrum and the way we pay for spectrum today. Well, we need to make sure that each company, each user of the spectrum pays for the slices of the spectrum they use. And if you put that as an incentive, then everybody will try to lower the spectrum they use because they want to lower their bill. Gas goes up, you lower your gas consumption. If you want to use more spectrum, you have to pay for it. Then you have an incentive not to use too much spectrum. What does that mean? Lower transmission energy. You don't want to transmit too much energy because then your collision domain increases and you'll pay for more space. You want to increase your MCS, your modulation and coding scheme, so you can transmit more data by using less time the spectrum. And you want to make sure that you don't have any collisions because that's a wasted spectrum that you will pay for. Today, most people, most entities using the spectrum don't pay per usage. They either pay a full amount and that's all, and then they can do whatever they want with it, or they don't pay at all, and that's all. So that's how you can solve this problem. Going forward to the why now, I think Ignas already showed quite a lot of details on how the usage of the internet and the wireless usage of the internet grows over time. That's more or less the same image here. It's exabytes per month, indeed. And we come from 2017 in around 120 exabytes per month. And we're now sitting closely to 400 exabytes per month in 2022. What is interesting, though, is the share of who is using what technology to share, to download or upload those exabytes. So the blue is the fixed access, so wired lines. The green is the fixed Wi-Fi access, so Wi-Fi is employed in our houses, for instance. The color is not very clear, but the blue is the fixed Wi-Fi from Wi-Fi only devices, and the black is the mobile. So we can see that in 2017, the fixed wire lines were like 51, 52%, while now they are only 30%. So there is a clear trend of going down. Most people now use their mobile phones or their mobile devices, their tablets, their laptops, and other devices that they can have with them. And that's where the main data load comes from regarding wireless access. And mobile plus Wi-Fi is now almost 70%. So wireless access means spectrum. Right now, we're using spectrum to transfer more than 70% than of the global overall traffic across the globe. That says a lot. And this trend will only continue to grow. We will have more and more wireless and less wired because everybody's using now devices that they can have with them all the time. One more thing, 5G is coming as well. It will also increase a lot the usage of spectrum. They already asked for specific sub ranges of frequency ranges, and they have got them. They are also asking for frequency ranges between 10 and 20 gigahertz. They will probably get some slices there as well. So more spectrum is coming into play, so we can have more speed, more capacity. I would say more virtual capacity, because capacity is only present if you can provide it all the time, and sometimes you can't. But still, 6G is coming after that. What will 6G want? Well, more spectrum, because then we will have needs for more capacity. We will need more spectrum and more spectrum and more spectrum. And as I mentioned already, the usable spectrum, the widely usable spectrum is up top to 7-8 gigahertz. More than that, you have to have issues with propagation. And that means they will try to steal spectrum from other applications. That could be ISM bands, that could be military radars, that could be anything else. But still, there will be a huge battle for spectrum in the sub-7 gigahertz bands. And can we solve that? No. That's the spectrum that we have right now. That's the main spectrum that we're using, up to 7 gigahertz. Even if we have terahertz communications, they cannot be used for the kind of application that we're using today. On the satellite domain, the same more or less picture is there. I have here a figure that was a projection at the 2018 to 2028 range. So at 2018, we had like 2.3K satellites orbiting the Earth. And now the projection was for 2028 that this will go close to 10,000. Well, that projection is already out the window. Only SpaceX already has plans to deliver 30,000 VLEO satellites by 2030. And that's only one company. I don't remember the name of the other company in the UK that was about to go bankrupt. Still, they got saved by the UK government. So they are also planning now. Yes. So they're also planning now to deploy tens of thousands of satellites if they don't go bankrupt in the near future again. That means that projection is completely false. We're not looking for 10K at 2029. We're looking at 30, 40, 50K satellites at that specific time. That's not a 300% increase. That's like a 1,300% increase. And all of these will require fixed allocation of spectrum. In the satellite domain, we're a bit more, let's say, lucky because we have also very directive antennas for links towards the Earth, so we can do spatial reuse a lot. And they also have the ability to have inclination, which plays a huge role in the interference they create and the interference they perceive on their antennas. So the space there is not just frequency, time, and space. It's frequency, time, space, and inclination. So it's even more easy, and polarization as well. So it's even more easy to avoid solving the problem. If you can avoid solving the problem, you just go in the frequency domain, in the time domain, or in the space domain. And you don't solve the problem of dynamic spectrum sharing because you can still avoid it by playing within those boundaries. But those boundaries are also fixed. They will not grow. There are no other boundaries that you can play with. So by the 1,300 range of increase, we will have problems, please. Mm-hmm. Mm-hmm. So the question is that there are companies like this, where they had plans also to deploy satellite dishes and in general deploying infrastructure, and then nothing happened. And the idea is if you have multiple agents in the satellite domain, deploying infrastructure and deploying satellites? How do you solve the security issue? To be honest, that's a bit beyond what we're looking at right now. Security is something that should be solved by encryption, by authorization schemes, by AAA protocols. There are solutions so far that are being used in the wireless domain in the terrestrial systems, and they so far provide quite robust security between the transmitter and the receiver, and also when you try to authorize a specific transmitter to speak to a specific receiver or join or disjoin a network. So security is an issue, but it's an inherent issue in general for all the communications, not just the wireless, not just the satellite communications. Even the wired communications today, you can very easily tap in one undersea cable and get the exabyte of data that are going through there, and then it's a matter of figuring out what they mean. Then it's where encryption comes into play. You have the bytes, but you won't know what they mean. So they're more or less useless unless you manage to crack a very sophisticated encryption algorithm. So the area of security exists everywhere, not just in the wireless domain. In the wireless domain is a bit more sensitive because you don't have to tap physically to a cable. You can just sniff the air and pick up IQ samples. But they are just IQ samples. You may be even able to demodulate them into bits, but still, if you cannot decrypt them, they are just bits. You don't know what they mean. So to summarize, on the satellite domain as well, the same picture exists. We see a huge increase in usage, and we need to figure out how we will make that work. They also use fixed tables right now between the operators. So I'm coming to basic sharing strategies that the regulation allows today in the world. I'm not going to go directly into specific regulatory solutions that are only applicable to the EU or to the States. I will talk from a research point of view. What are the three main, let's say, approaches on spectrum sharing, on sharing frequencies? So first of all, and well known are the ISM bands, where everybody can transmit and receive data in the ISM bands as long as they follow specific rules. So those rules have been applied by the regulatory bodies like ETSI, like ITE in the United States, and you are able to access that specific part of the spectrum only if you follow specific rules like listen before talk. So you need to sense for energy, and if you see energy is there, it means somebody else is transmitting, and you have to take a time off, not use the spectrum until the energy is dissipated, and then you know the medium is free, and then you can try to access it as well. This kind of simple rules are working so far, and that's actually what makes Wi-Fi work. Wi-Fi is working mainly on LBT, and all the ISM bands, 2.4 gigahertz and 5.6 to 5.7 gigahertz also is working based on LBT. It's a well-known MAC level solution that allows to solve specific problems when you have technologies that more or less have the same capabilities and capacities on accessing the medium. Fairness is also always a problem there that we still haven't solved. You have also cases like the CBRS in the United States. CBRS is a very first effort, let's say, of the United States to go towards dynamic spectrum sharing. What do? They figured out they have specific frequencies like military radar frequencies, satellite frequencies, and terrestrial systems that they can reuse those frequencies when a radar is not there. A radar is not always in the harbor. A ship is not always in the harbor. A radar is not always operational. So why have this 3.5 gigahertz spectrum range completely empty if nobody is using it and you're not taking advantage of it? And that's what CBRS is, trying to reuse specific frequency ranges that are not being used all the time at the entire range of the United States mainland. And it's quite successful so far, I would say. On the other hand, we have licensed shared access, so licensed bands, but not only with one licensee, but multiple licensees. And then you can have either main operator and secondary operators, or one main and multiple secondaries, or maybe even two mains and multiple secondaries. It's all about how do you play the game. But the end result is multiple entities have paid for using that specific spectrum, and then you have to allow them to come in and use the spectrum. But again, fairness is an issue. And the only way you can solve fairness is by having a very strict, let's say, approach where you have a primary user that you know he can use whatever he wants, and then a secondary user coming in just to fill the gaps. That's the only way you can have fairness, because you have a primary that can do whatever he wants, and a secondary that is just there to increase the efficiency of the spectrum, but not actively take as much spectrum as he needs. If you have two mains, the fairness problem becomes a real problem, and you have to solve it by applying rules that are relevant to just fairness from a scientific point of view, or economically, who paid the most, he will be able to use most of the spectrum at that specific time. One type of licensed shared access is what happens today between 4G and 5G installations that are being used, that are being deployed by the same operators most of the times, so they can very easily share information between the 4G and the 5G deployments, and then based on the load between the two systems, can change frequency being used by 4G systems or 5G systems and vice versa. But that can happen only because it's the same operator, which he has no problem sharing data with himself. And then he can manipulate, he can monitor, and he can manage both systems at the same time. And that's how he's able to create what we call licensed shared access. But when you have multiple operators, then problems arise, because most operators don't want to share information of their spectrum usage and their data usage and the load that they have over time within a day with competitors and in general with other entities. They consider that to be a no-no. And that's maybe something we need to figure out how to solve. We need to be able to share data if we want to go towards dynamic spectrum sharing. So how do we do it then? Okay, we've seen the status, we've seen what's going on today, we've seen possible solutions. How do we solve it? We see two main families, let's say, of solutions. One family is the uncoordinated systems, when you have systems that are exploiting specific capabilities, like the primary secondary users approach that I mentioned before. You can have databases and models figuring out if somebody is transmitting from point A to point B, what is his collision domain based on a model, and then based on that model, figure out who else is getting interfered, and based on the transmission power as well, and then creating a huge problem that needs to be solved in runtime. So then you can say, okay, then you are transmitting at that specific target energy power. Make sure you don't exceed that point, because then you'll interfere. We think you'll interfere with that other transmitter. That's the approach of databases. It can work in a small scale, in our opinion, but it doesn't scale up. You will never have a database that covers the entirety of Europe. Do you need it? Probably yes, but that database doesn't need to know everything that happens in Europe. You need a local database that knows what happens, not even in Antwerp, but in some small part of Antwerp, not even in Ghent, in some neighboring Ghent, please. Yes. Yes. So the question is, isn't CBRS also a database-based approach? So it has two, let's say, enablers. One is databases, and the second is also spectrum sensing. So they have the ability either to get the information from a database. Is there any radar in my vicinity? Then if no, this is the answer from the central entity. I can use that frequency range. But they also have local spectrum sensing in case the connection to the entity is not there, or the entity is offline, or something happens in the communication between them. So they have like a backup plan to be able to sense and see if radar is there. Radars are very periodic signals, so it's quite easy to figure out if they are there. So indeed, they use databases as a first approach, but they also have a backup plan. There is also, as already mentioned, beamforming and beam hopping. What do they do? How do they help? They actually help to avoid the problem again. They are not solving the problem. They are making easier to spatially reuse spectrum, because your transmission cone is not a cone, it's like a laser line, so you're not interfering easily with others. Is that a solution? In our opinion, that's an enabler. It can help you avoid the problem. Does it solve the problem of spectrum sharing? No. It only makes it easier not to try to solve it. And that also will fail really soon in the future. Spectrum sensing, does it help? In our opinion, yes. As I already mentioned in our previous slides, knowing the local ground truth in any receiver by spectrum sensing is something that will help the receiver make proper decisions and make sure it doesn't interfere with anybody else, while also acquiring the spectrum that he needs based on his local load. And that's one axis that I haven't talked about at all, the load in its transmission, in its link. Based on the load, you have to acquire spectrum and then release it, not use it for 20 minutes just to transmit one FTP file for a few seconds and then just keep the link active because somebody might send something through. You have to avoid using spectrum without actually sending application layer data. You have to have a very quick reaction on your user load versus your spectrum sharing. Spectrum usage has to follow user load and not just have static capacity waiting for that big spike of data that might come in the moment somebody starts to download a 4K YouTube file. The second family is the coordinated systems using cognitive techniques. And there we have the ability to have central control entities where they are some kind of message brokers. They don't use database approach. That's the difference between this approach and the database approach. They are like message brokers, and they only send the messages to the entities that are relevant to a specific transmitter. So if I'm a transmitter, I'm going to ask that central entity, which nodes are in my local collision domain? Can you tell them that I want to transmit in that frequency range? And then he will come back to me. I sense based on my models and in my database that there are like 5 nodes. Those are their MAC addresses. Talk to them and figure out collaboratively what's going on in your local collision domain. The last is decentralized coordination and management protocols where you don't have a central entity. And in our opinion, this is the way to go. You need to be able to solve the problem locally without having the latency problems of talking to some central entity that might be tens of hundreds of milliseconds away, and then waiting for the response to come back, and then try to apply that response in your local spectrum usage. You have to solve it locally. So collaborate with your local neighborhood, figure out what is there, and then figure out how to solve the interference problem between them in the frequency time. Space is not a factor there because you already know that they are in your collision domain. You are transmitting a hello message. You're saying, hey, who is hearing? Whoever responds means he is in your collision domain. Solve it with him. You don't need to solve it with anybody else. So let's say one of those solutions comes into play and we have regulators coming in and saying, okay, we're going to open a band and we're going to allow everybody to come into that band and play as long as they follow these specific rules. What are the rules? One of the rules that are being applied by the previous solutions. What do we gain? We're able to resolve interference issues for known and unknown sources locally with very low latency, with a very fast control loop. We're able to reuse spectrum slices. You can reuse them because different transmitters can use the same frequency slice because they are not in the same collision domain as others. And that is completely transparent. You don't need somebody to decide that. By sensing your local spectrum, you know if somebody is using that specific spectrum slice. You don't need any engineer or regulatory device or regulatory body to come in and say, you can transmit there, you cannot transmit here. You have to follow this man-made fixed rule. Why? We have 7 gigahertz. Let's try to use them at every space in Earth at all times. That should be enough to solve all the capacity problems that we have for the next 10 years. But we're not doing it enough today. But we have, of course, adoption challenges. How difficult is it to come in and say, we're going to change the way we use spectrum today? I think the biggest problem comes from the conservative approach that we see today in the community of wireless spectrum usage. Regulative bodies and the industry stakeholders are very conservative. They don't want to change things, especially stakeholders, because they are the stakeholders. They make money out of it. Why would they want to change it? It's a status quo. Everything is fine. Let's wait until everything breaks. And then, yeah. That's good to know. Mm-hmm. So some companies are really seeing the problem and they're trying to address it. I hope so. I hope so. The best cooperation methods that provide the best results, they also require cross-operator spectrum usage data. So if you want to collaborate between deployments of different MNOs, they have to share spectrum usage data between them. And that's a big no-no right now. So we have to convince them that they have to gain by sharing their usage, the spectrum usage data with their competitors. They all will gain as a community, and the society will also gain if we manage to follow that through. But I think that's the biggest problem towards dynamic spectrum sharing, especially in the terrestrial systems. The same applies also for satellite domain. The satellite operators are very reluctant to open an access point, an API, so others can read their load at times, the transmission cones and everything that is relevant to dynamic spectrum sharing. Some satellites. So the question is that satellite systems are fixed in frequency, and it's not possible to change them. So I would say that's true for geostationary satellites, because they are actually lighting, let's say, half of Europe. So it's not easy. It's not that they cannot do it. You can do it by having a protocol between the receiver and the transmitter. But right now that thing doesn't exist. So everything is fixed. Your satellite, let's say, receiver in your house is fixed to look at a specific frequency with a specific modulation coding scheme, and everything is fixed. If there is the capability of two-way communication between the satellite and the terrestrial system, then you can actually have a protocol between them, so they can also collaborate and exchange information on, okay, in the next super frame time, we're going to change that frequency from that to that. And if transmitter and receiver do it at the same time, you actually have a completely transparent change of frequency without any one of them losing connection. I'll show you some specific results to prove that this is possible. Surely we need to do what we call here software updates. We need to change, for instance, the MAC in the satellite domain, which in most cases doesn't exist. There is no MAC. It's continuous transmission. We need to have hardware upgrades. For instance, SDRs could play a huge role into having reconfigurable hardware on the satellites, so we can update the physical layer, but also the MAC, and be able to use these continuous transmissions. That's a must if we want to have dynamic spectrum sharing. You can't have one specific client or entity just beaming in a specific frequency without sending anything, or even by sending data all the time without having any ability for somebody else to step in. If that's the case, if that's how we design physical layer systems, of course, there is no capability to do any kind of spectrum sharing. But we have these continuous systems. The fact that the satellite domain has chose not to use them because so far what they have works, and they don't need to change that, that doesn't mean we don't have the technical capabilities of doing so. And I will show a result on that later. So what is the EU doing towards dynamic spectrum sharing? Yeah, a very easy slide. We are discussing, we are wishing, and we are hoping. I think that's all. And to be a bit more precise, so I'm not very, criticizing the EU. We have some Horizon 2020 projects that tried to go towards dynamic spectrum sharing. Maybe not exactly in the approach or in the way we see dynamic spectrum sharing, as a very generic problem that, in our opinion, could even be a new OSI-ISO layer below the physical layer, that is spectrum sharing. Before using your physical layer, you have to find a spectrum slice. We need a new layer in the ISO-OSI system. A generic layer that will solve how do you access the spectrum. That is not where we are today. So there has been approaches like, how can I make LTE and Wi-Fi work together? That's dynamic spectrum sharing. Is that a generic solution? No, that's like trying to get two players working together. How can I make Wi-Fi with Zigbee, with Bluetooth, with whatever work together? We have like 40 standards today. If we try to create solutions one-on-one or one-on-two, how many are the multiple standards that we need to create now to be able to have all of them being able to operate at the same frequency range? The number is huge. So we need a generic solution, not a solution based on pairs, on duals, this technology and that technology. There is, of course, the RSPG EU group that on 2021, they tried to create an opinion, let's say, of themselves on what's going on with dynamic spectrum sharing. And in order to do so, they talked with various stakeholders in the EU continent. And of course, they got a specific opinion. The thing is, when you talk with the stakeholders, they will tell you what they want to do, and they want to continue to make money, in our opinion. So they don't want to change something if it still creates money for them, and they can still handle the situation of spectrum fixing, paying 200 million for getting a few frequency ranges, and they can make a few billion out of them. So that's a very profitable way of working. Why change it? The thing is, do we need to wait until everything hits the wall and only then change? Or can we see that the wall is coming really fast towards us and we need to change as much as possible, as soon as possible, or at least prepare for the change? And the European Space Agency, in our opinion, is quite interested, is looking forward to dynamic spectrum sharing. They see the capabilities, they see the advantages, and they have already worked with us. And they actually pushed us to go forward with them in a simulation study to figure out, can dynamic spectrum sharing help the satellite domain? And the results were quite optimistic. I hope that the ESA can have a bit more influence on the European Committee approaches, because that would really help pushing forward dynamic spectrum sharing. So some results, because we had a lot of talk on, can it be done? Is it possible? Maybe that's like science fiction. Well, it's science. It's not science fiction. So what we see here is the project Wishful, that ended 2018. So it's already 5 years ago, where we were able to have cross-technology synchronization and three-weighted DMA scheme, so solving coexistence and dynamic spectrum sharing on the time domain between three very different technologies. What you see here is an actual spectrum analyzer snapshot of a signal in a specific frequency over time in milliseconds. And you can see different packets being very nicely separated in time. That's why we call that a three-weighted DMA schedule scheme, between Wi-Fi packets, LTE frames, and 15.4 frames, Zigbee frames. So you can see clearly the LTE packets. They are the longest ones, 5 to 10 milliseconds most of the times. Those are the very short Wi-Fi packets, and those are the very short, medium short, let's say, packets of IEEE 802.15.4. We call it Zigbee. That's the, let's say, empirical name. So solutions on the MAC layer like this one exist already 5 years from before. Is that a solution that can be generic? Yes and no. I would say that's a solution that can work most of the times, but you need to have a beacon, so an energy signature in the air that all technologies can recognize, and they can synchronize based on that. So again, it's up to the regulatory committees. If they want to go that way, they can say, okay, then in every aspect, in the entirety of Belgium, let's say, or Netherlands, we're going to have 20 beacons sending these signals out all the time. And then, guys, it's up to you to figure out who's going to go next after the beacon, and then do a spectrum slice on the time domain. But that's sharing only on the time domain. So that's like initial results. Can we make different technologies share the spectrum on the time domain? The answer is yes, of course. But then we moved forward and we try to see, can we do generic sharing between completely unknown technologies? So in the DARPA Spectrum Collaboration Challenge, the game was, you put 5 unknown technologies, different PHY, different MAC, in the same collision domain, and you allow them to collaborate by a collaboration protocol. So they exchange data on the spectrum usage that they do, and then you have some either expert algorithms, or even better, some AI neural networks that figure out what is the best solution, how can you collaborate with the other technologies and be able to share the spectrum in runtime. So all of those experiments were executed in the Colosseum. It was a huge infrastructure that DARPA set up the cost was around 20 million just to set up the Colosseum. And the idea was that you can emulate everything on a IQ level from PHY all the way up to the application layer. So the actual devices that we had running in the Colosseum, you could also set them up outside and have a communication between them in the real world. They were not simulated devices. We were only emulating the physical layer on the Colosseum. All the rest was a full working system. So what we see here is that we could have scenarios for avoiding active radars, passive satellite incubants, active satellite incubants. We could have a monitoring spectrum in runtime, as you see in this figure here, where our transmissions are the big slices, and that in the middle is an incubant that we are trying to avoid. And you can see clearly here that when the incubant was active, we were not transmitting. The distance between the incubant and our active transmission was in the range of tens of milliseconds. So we were able to have only a safety gap between the incubant and our, let's say, secondary user, with a security gap in the time domain of 10 to 15 milliseconds. So that's the waste of trying to do dynamic spectrum sharing. You could have the monitoring of the spectrum and be able to identify even the technologies that are there. You could see this is a Wi-Fi technology, this is a LTE technology, and so on and so forth. Because the system was unknown technologies, we could only fingerprint them, so we didn't know if it's Wi-Fi. There was no Wi-Fi. Everybody was using some exotic PHYs and some exotic MACs. But we could still see this is team 1, team 3, team 5, team 10. And that was happening in runtime using AI. We could even identify the incubants, like here. You can see clearly in this representation that the incubant from the IQ samples, we could actually see through the AI model exactly where it is in time. And the same applies here, although the incubant was buried behind transmissions from other teams that were actually interfering with it. We could have a satellite incubant saying, don't interfere with me above this threshold. And you could have 5 teams trying to transmit without passing the threshold. The third phase was always a failure because DARPA wanted to see if we were able to go beyond the limits of that at that time. So it was a very harsh environment. Even the slightest transmission would actually trigger the incubant. But in the first 2 phases, you can see that 5 teams were able to protect a satellite incubant. The same applies here. And one thing that I want to make clear, this figure is a scaling experiment on the slot allocation protocol that we actually used during the DARPA collaboration protocol challenge, sorry. So that figure shows that although in the DARPA collaboration challenge we worked with 10 nodes per team, we said, is that scalable? Can we go to 500 nodes, to 1,000 nodes? So that figure here shows what happens if you go to 100 nodes, 200 nodes, 300 nodes, 400 nodes, and 500 nodes. And if you start from a clean environment without any slot allocated, without any spectrum slice being allocated, how much time will it take you? And if you increase the scale, will you also see an increase in the time you need to use the spectrum? And the red line says no. It's completely scalable because your delay from time 0 until you have the spectrum fully allocated between 100 nodes, 200 nodes, 300 nodes, 500 nodes, without collisions, without interference. So they would completely solve the problem and say, okay, now we have a fixed allocation scheme between us, and from now on to eternity, we will have 0 collision between us. It took 60 seconds. So that's once delay. After you reach that stable point, even if you have a newcomer coming in, he will only have to solve his local problem with his local neighborhood. So that will be solved in a matter of milliseconds. You can see those papers that I have here as reference for all of those technologies if you want to see more details. Most people don't believe what we have in the paper, so I will try to show you a video of the representation of what's happening in a system that was running in DARPA. So what we see here is the time domain and the frequency domain. We had 4 channels and 20 time slots, and how the system, one specific receiver, how he perceived the spectrum at intervals of 20 milliseconds. So every 20 milliseconds, he was sensing the spectrum, and the color in each slot says how much energy I saw in that slot at that given time. And whenever you see numbers are the selected frequency spectrum slices for this specific transmitter, so he can set up a link with a specific receiver. And if you have the time to look at closely after the presentation, you will see that the number that says 100%, that's the packet success ratio, means that we were able to pick up these specific slices where they had 100% packet success ratio. And if somebody else, some bad guy would come in and try to use that spectrum the same way we did, we would see that falling down, we would jump out and go to another slice that was free. And by doing so, we were able to keep very strict quality of service requirements on the application layer in the range of a fixed maximum latency of 200 milliseconds and packet success ratio in the range of 99 to 100%. That was happening when 5 different technologies, agnostic between them, were sharing the same collision domain with 10 nodes each. So 50 nodes running in the same collision domain. And that was the result. Regarding the incubants, I mentioned something about being able to avoid actively incubants. Yes, I'm finishing. The incubant is visible in some frames, like, let me see, like this one. And you can clearly see that although we're using that specific channel, the moment the incubant is there, we magically disappear. And then when the incubant is not there, we continue to reuse the channel. And when the incubant is there, we disappear. That was happening in runtime. We were able to identify the incubant. It was a radar, figure out the periodicity of the radar, train a neural network with it, and then be able to avoid it with a gap less than 10 milliseconds. So we were able to stop our transmissions 10 milliseconds before the incubant was there, and then we were able to continue. That's real machine-to-machine collaboration. No human hand was in place. And all of those problems were solved by the same system. We didn't have multiple systems that were solving each problem on its own. We were always uploading one system to solve passive incubant, active incubant, multiple technologies at the same time, satellite incubants technologies there. All of the 12 or 13 scenarios that DARPA had in place, they had to be solved by the same system. So that was a generic solution, not a hand-picked, man-made solution per problem. For the ESA Codesand project, where we're focusing on the satellite domain, I don't have a lot of time, so I will try to be very fast. We used 3 major techniques: spectrum sharing, spectrum sensing for our coordinated approach, collaboration protocol, so changing information between the transmitters and receivers for decentralized and coordinated approach, and a hybrid solution that we were using both of them to see if you have 2 different approaches, will they give anything better than just using one of them? And the idea was to reuse spectrum in the download KA band, 17 to 19 gigahertz, and on the uplink, again on the KA band from 27.5 to 29.5 gigahertz. So we had a baseline scenario with no spectrum sharing, and the downlink time was around 80%. So 80% of the time we had links operational, we had 20% downlink because of interference between the nodes. The scenario was quite complex. We had multiple nodes running on the terrestrial space, but we also had satellites running on the air, and they were also getting inline, so they could create inline interference between 2 or even sometimes between 3 satellites. So we had to be able to solve the inline interference between terrestrials, but also satellite systems. And the overall result, the moment we applied DSS1, which was just spectrum sensing, was close to 100%. So we solved 19, not 20%, but 19 point something percent of the collisions during runtime. DSS2 a bit less, and DSS3, the collaboration between the two, again, close to 100%. That means we were able, during runtime, to solve the collisions and avoid having the huge interference that would create a lot of gaps in the active links between the transmitters and the receivers, both on the wireless, on the terrestrial systems, but also on the satellite systems. So that result is the average of both and satellite systems and terrestrial systems. More details again in this paper in the MDPI journal, which has all the scenario setup and very nice figures on exactly how the scenario looked like. Takeaway message, my last slide. Thank you for your patience. So we argue fixed spectrum assignment is not sustainable. We have to understand that, we have to see that before it actually happens. Now we are still have the time to prepare, and I'm not saying we have to change everything, but let's start small steps. Let's make an ISM band, which is not an ISM band, but it's a shared spectrum band anymore, with different rules, with a collaboration protocol, maybe, with active spectrum sensing, why not? With a database for starters, sure, but let's start somewhere. Let's start somewhere so we can prove to whoever is very conservative and doesn't want to change, that if they change, they have something to gain from the spectrum point of view, and then the regulators come in and say, you can also have something to gain from the economic point of view. So you have an incentive to change. We also say very clearly, ground truth is on the receiver. Whatever solution we design and we try to implement, we have to take into account the ground truth on the receiver and not just some modeling approximation of the reality. Modeling is good for papers, and that's coming from research, from a researcher. Modeling is good for papers, it's not good for reality. Let's try to avoid MATLAB, let's try to avoid OpNet, model sim, whatever else you want. Let's try to go to proof of concepts and prove that solutions like that can really work in the real world. We have to push standardization. We have to push standardization to put some rules on dynamic spectrum sharing bands, so then we can have a real spectrum sharing band in the near future. That has to be PHY agnostic. If we follow our, let's say, proposed approach, let's make dynamic spectrum sharing a new layer in the OSI model, that means we don't care what kind of MAC you use, what kind of PHY you use. The spectrum sensing, the spectrum sharing has to happen before accessing the medium, before using your PHY. So it has to happen even beforehand. So next steps, let's go to proof of concepts. Let's use theoretical studies, use the results, but let's go to try to prove in real life that these things work. We need a regulated DSS band. We have to push for that. We have to push the regulatory bodies. We have to push the EC. We have to use players like ESA to push the EC so we can move forward and have one band in the range of 50 to 100 megahertz. We don't need more than that for starters, just to get everything up and running. And we also need to figure out, do we want centralized approaches or distributed approaches? I'm always in favor of distributed, but that's again something that we need to prove in reality. And that's all from my side. Thank you very much for your time and patience.
All the time, but still I would like to see if there are any questions,
Yeah.
in particular from the online people.
Yeah, there are some questions and comments. It may be even that the persons that have raised the question can even do it by themselves if they unmute their phone, starting from Rogier Noldus. Would you like to? Yeah.
Yeah, okay,
You had
thanks.
some
Can you-
comments. Yeah.
Good. Okay. I thought I picked up that you mentioned that operators within one geographical area, for instance, the Dutch mobile operators, they would be sharing the same frequency slot. So we know dynamic spectrum sharing, but then so far as I know, it is used by one operator. Then do I understand it correctly that a particular frequency slot may be used by a multitude of operators?
Yes, correct. That should be the way forward. So the idea would be that you have to pay for the spectrum you're using. And if your capacity needs at the one specific time are X, then you should be able to have X spectrum, but it doesn't have to be in one specific frequency range. It can be in a wider frequency range where you can reuse and use spectrum arbitrarily.
Okay, yeah, good. So you would effectively pay for the usage of the spectrum.
Correct.
Yeah. Okay. Good. Okay. That's clear.
Which will also incentivize efficient use of spectrum.
Yeah, for sure.
There is also a question here coming from Sitse van der Gaast. Sitse, would you like to unmute your microphone and raise the question yourself?
Yes, thank you. Yes, I was wondering how to ensure that a protocol for information exchange that supports dynamic spectrum sharing is as neutral and simple as possible and can and will be supported by a very wide range of devices. Because, well, a standardization body can make up such a protocol, but well, stakeholders in such bodies are always trying to optimize their own benefits. And also such a protocol has to be future-proof and backward compatible. Or are there already feasible candidate protocols? Of course, we know of ecosystems like Wi-Fi where it well, goes reasonably well, but this goes beyond that. What do you think about such things?
Correct. The collaboration protocol is one of the big enablers, let's say, of dynamic spectrum sharing, if you go that way, if you go the collaborative way. And what do you need to share through that protocol is indeed a big problem. So, for instance, in the DARPA Spectrum Collaboration Challenge, the main things teams were sharing between them was the geometry of the transmission cones that they had active, things like the duty cycle at specific given time periods, and also their intended spectrum for the next X, let's say, seconds. So by sharing information like that, we were able to collaborate between each other and figure out decentralized, in a completely decentralized manner, how to share the spectrum without having interference. That's just one solution, and surely standardization has to come in. We have to set up a working group that will put down the problem and figure out how to efficiently share data, also taking into account security issues and possibly big operators, concerns regarding security and data sharing concerns. So surely that's a problem, but it's not a problem that we cannot solve as long as we focus towards that way.
Thank you.
Thank you.
Okay, I think we will have stop here.
Thank you very much. Thank you very much.
Time. I'd like to invite Frank for talk. Frank, I think we need to get your presentation on there. Yeah. Frank is working as an advisor at Rijksinspect Digitaal.
Yes, please, you have to talk close to the microphone.
So Frank is advisor at Rijksinspectie Digitale Infrastructuur. Since January 1 is that entity that replaces Agentschap Telecom. He's been working already for 25 years on frequency and telecommunication issues. He helped to establish telecommunication policies for regional netbeheerder, and is involved in setting up a private virtual network operator in which that works on IoT, Internet of Things. He's also active in a project that looks at, and this is directly related to this, to the opportunities and possibilities of dynamic spectrum management and sharing. And he's also working on energy transition, a different topic. So he's a man with also many interests, I would say.
That's correct. Thank you. I think I'll touch a lot of things on of Spiele's presentation. Well, let's start. The original, since the 1st of January, we have this name, Dutch Authority for Digital Infrastructure. We used to be the Radio Communications Agency, so radio is still a part of the digital infrastructure. What you call dynamic spectrum sharing, we call dynamic spectrum management and sharing, but I think the concept is the same. I'll touch very briefly the history of spectrum management because it's very interesting. You see history repeating, of course. I'll touch the increasing demand and possibilities of frequency use. Sharing, that's basically, it's not a new concept, so we can learn a lot of things which are already in place. And then we'll go specifically to dynamic spectrum management and sharing. I'll talk about the concept we thought about, and specifics, and the pilot we're working on at the moment. And of course, some future enhancements. Because compared to the previous presentation, we're only touching a little bit of dynamic spectrum management to make the first steps. And that's really what they are, first steps. For history, and of course we see things repeating. I don't invite you to read the left-hand side. It's about telegraphs crossing borders, and it's about standardization. From France to Germany means sending it to a border station. The message has to be translated and sent in German further. So that's has to do with standardization. And we already mentioned standardization on protocols to enable dynamic spectrum management. It's as old as telecom. Another thing, 1906, I think it's the first radio telegraph conference, and it's maritime driven because there was an issue with Marconi equipment, the Telefunken equipment, especially with operators. Marconi operators were not allowed to talk with Telefunken operators because of market power. And we see that again if we're talking about dynamic spectrum management at the current situation. Just briefly, our history and spectrum management. And since the first radio regulations, we see that spectrum is regulated in blocks assigned to specific use, for instance, mobile, 150 to 180 kilohertz. So that's a long time ago. And since then, that's a few hundred years ago, of course, we've seen some interesting things which enabled mobile communication. For instance, 1987, the introduction of mobile communications across Europe, which my children nowadays find as normal as anything. You just can travel Europe and have your mobile with you, and it works always. That's not that long ago. On increasing demands and possibilities, a lot has been said. The huge demand for spectrum, of course, by having better semiconductors, more integrated circuits, you could use higher frequencies. Mobiles getting smaller and smarter. But also, and Spiros mentioned modeling. Modeling gives you insight in what's happening in the spectrum. So if you have better modeling possibilities, you get better insight, although it's always a model. I have to agree with that. For instance, the pictures, these are broadcast coverage areas a long time ago. There used to be circles, just made 36 calculations around a transmitter to calculate coverage. But when more data came available, like clutter and height data, and more computational power, of course, you can make calculations based on the models in areas from 100 by 100 meter. So it gives you more insight in what's happening and what's possible. But then again, sharing is not a new concept. I think, Spiros, you mentioned most of these dimensions where you can share spectrum, frequency, spatial, so just put them apart. And time, this is based on a ITU standard. And these three were already in there for 20 years or something. And there's another one they call signal separation, and that's they put everything in signal separation, which doesn't fit the other three. So, for instance, reduction of interfering power, they say, well, that's signal separation. And that one has evaluated the last years to care for better spectrum sharing. So it's not new, but it's getting better and better. The lattice on the right is out of some spectrum planning of the 60s. And it basically already gives you a certain pattern how to reuse frequencies in spatial and frequency separation. So basically sharing, it's not a new concept if you look at it that way. Two examples. Broadcast frequencies can be reused as long as the distance between the transmitters is large enough. Or one is which is also heavily used, wireless microphones using frequencies between TV service areas. They're low power devices. They do not interfere broadcast reception, and it's only local use, so they don't get interfered by TV service areas, but they do share the same frequencies. So again, not a new concept. What happened when I started working with colleagues, I think about 3 years ago, on this subject? One of the first things we got touched was the Spectrum Collaboration Challenge, which gave insight in what you could do on a greenfield situation, what can be done on spectrum sharing. Very inspiring. So that got us thinking about how to go further. Speakers also mentioned the Radio Spectrum Policy Group. Not very positive about the ambitions, but they published in 2021 papers about sharing and the need for sharing spectrum, because it's quite clear there's not enough spectrum if you don't share in the future. I'm not sure if it's readable on the right. That's one of the things they mentioned in the report, and they encourage member states to come forward with proof of concepts to show dynamic spectrum sharing is a possibility to work in the future. So we took that challenge. Sounds easy. And asked, in this case, Stratix to do a study for the Netherlands to come forward with possibilities to do spectrum sharing. And we asked specifically some frequency bands where we can use pilots or proof of concepts. And they come up with a list. UHF, basically use case wireless microphones and digital broadcasting. 3.8, 4.2 gigahertz, which is a band currently primarily used by fixed satellite reception. 6 gigahertz radar band, 8 to 12 gigahertz, and 26 gigahertz. But at the same time, or a bit later, the RSPG had a mandate to the SEP to study shared use of the 3.8 to 4.2 gigahertz band. Specifically, they mentioned local and vertical use. So that's not used for commercial operators, but for private networks. Putting that all together, we thought, well, we have to figure out what to do with that band and to see if we can work on dynamic spectrum management in that frequency band. The question is what I mentioned with vertical use. That's the complete chain from the use case until the equipment and antennas is in the hand of one party, like a private party owning their own equipment, having their own use case without using equipment from operator or frequencies from operator, all in one hand. And nowadays you can compare it with using as a company using public networks. Then there's a split in the vertical chain. So you have your application, but you're using the equipment and the frequencies of a third party, from a network operator. The vertical use is having the complete chain in one hand. That clear enough? You're the owner of the equipment, you install the antennas, and you have the frequency space, and you have the application. I think that's a good example. C2000 can be seen as a vertical user. They have their own spectrum, their own equipment, their own portable phones. Yeah. On the frequency mentioned, 3.8, 4.2 gigahertz. I mentioned there's a primary user at the moment, especially in the Netherlands, and it's fixed satellite reception. It's the downlink satellite to Earth, and they are using the full 400 megahertz of that band. And even if you ask them, they're using more than 400 megahertz of the band. That's interesting. And that's because they use large dishes, and when satellites are far apart, they can use one dish to the east, the other one to the west, and they can use the same frequencies in both dishes. So they even use more than 400 megahertz in the 400 megahertz band. And the duty cycle is 100% of time. So not much to share that situation. And the last thing, they require a lot of protection. It's larger than 99.995% of time. So we thought, well, what's possible in that frequency band to use by other parties? We found that, and that's the main part. I'll come to that later. That's the main part why there's so strict protecting. In this frequency band, there's the possibility for ducting. It's a propagation situation where path loss decreases a lot. For instance, in the Netherlands, you get a certain decrease in path loss of 60 dBs, depending, of course, the path. That means that signals which you are not normally able to hear or to receive gets received very loud in a certain point in time. That makes it interesting to share. First on ducting. Colleagues of mine did a study, did measurements across Netherlands in the 3.5 gigahertz band, and they studied the ducting phenomenon. The top picture is ducting, which is received in another part of the Netherlands by a transmitter, which is placed in Goes, the southern part of the Netherlands. And you see in the graph the path loss, which is normally around, well, roughly 215 dBs or something. And depending on the fact whether there's ducting or not, you see, especially the 1st of November in 2014, you see a dip of roughly 60 dBs in the path loss. It's very rare. It happens once in a while, and we're not able to predict it yet. So it happens, and it mainly happens during nighttime, but not always. And it happens more in summertime than in wintertime, but it's not predictable. That makes it very interesting. If we compare that with the protection of the satellite station, which is located in Netherlands in Biddinghuizen, the middle of Netherlands, they're requiring the high percentage of time protection. Because they want protection against interference also during the ducting, when ducting occurs. And that's the high level of interference, which only occurs very little amount of time. If you do that, you get the exclusion zone of the top picture. Of course, these calculations are made with some kind of reference transmitter of 5G interfering with the ground station. And if you look at that, there's no possibility to apply a 5G system in the Netherlands in this frequency band without disturbing the ground station. But it's based on the model to protect them for the very rare situation of ducting. That means that if there's no ducting present, the propagation loss is very high.
Excuse me.
Yeah.
There is a question regarding slide 10, just because I think the speaker, yes.
Yeah.
What is the thing? At what distance does the ducting phenomenon typically occur?
Sorry, what distance it occurs?
Yeah, that's a question.
Yeah. Okay. I've not done the measurements, but it was a setup. In this case, the picture you saw was from Goes to Buren, the north of the Netherlands, which is roughly 250 kilometers or something. And there were also measurements half of the distance, and it also occurred over there. So it occurs somewhere between, we guess, 100 and 300 kilometers, something like that. Could be more, but we don't have measurements of a larger distance.
Okay, thank you.
Yeah.
Yeah, I'm not. It is not from me. It's from one of the
Okay.
members of the online audience. Thank you.
Back to the possibilities for sharing. If there's no ducting, we could use 5G system in a large part of the Netherlands. The top picture is because of the classic way to protect services. The receiver at Biddinghuizen has to be protected against interference even if it's for a very short amount of time. So there's a lot of possibilities to share, as long as we don't allow to use 5G systems during times of ducting. Okay. So we start thinking about, well, how can we work on this? This is one of the first schematics we drawn intern. On the left-hand side, you see the local private networks, which can use this frequency band. And on the right-hand side, we see the satellite earth stations, which has to be protected. And then again, and I think that's a good match with the previous presentation, this one is also receiver-centric, because we look at the location of the receiver, the satellite dish, to see if we receive interference from 5G base stations. And if that's the case, the concept is to reduce power of the base stations. So it gets some kind of control. Difficulty in this case is that in this frequency band, the satellite ground station is using the full field 400 megahertz. Other part of the concept we did not go into detail yet. That's the left-hand side. Of course, you want to have multiple private 5G networks being able to access the spectrum, and of course, you have to have a mechanism how to deal with that. We did not. It's form of the concept we thought about, but it's in the pilot we left that out because it's very difficult to get a pilot without doing a lot of simplifications. Picture of the pilot we try to set up, and we try to draw the control loop. On the left-hand side, there's the local 5G network with an antenna mast, transmitting also in the direction of the right-hand side where the satellite ground station is, and we're putting there receiver, sensing receiver, which senses the interference from the 5G base station. It goes to the chain, will be processed, and the power of the base station will be reduced when interference occurs. So this is the basic concept we thought about. Well, at least it's one step towards more dynamic spectrum management. Of course, as I mentioned, we have to assume, have a lot of simplifications. The left-hand side is the picture of the actual ground station, having a lot of dishes. And the possibility of interference will be higher when the dish is directed towards the 5G base station. But that will complicate the pilot very much because you need a lot of information of the operator to see where his interference levels are. So first step, simplification. We made a model of the ground station, which is basically the worst case situation. Simplification, but it makes life easier. And then, of course, we assumed also the full 400 megahertz used in this model. When you have more knowledge of the actual usage, you could say, well, only part of the frequency is used by the dish which is looking towards the interferer. So the rest of the frequency band can be used. For usage simplification, everything is used. Yeah, they will. This operator is using, I'm not sure if they're using every dish for this frequency band, but this is totally no Inmarsat. This is fully commercial. It's a fully commercial station. They're providing worldwide services for internet connectivity for ships on board of vessels, things like that. Not Inmarsat, it's commercial. The company is called Speedcast. And of course, they're using a collection of downlinks, but they're also using 3.8, 4.2, full 1 megahertz. And of course, and that's what we assume. And of course, you can make finer calculations or finer measurements if you know more about where the dishes are pointing, which frequency they're actually using, because the one dish is using 50 megahertz, the other one is not using another 50 megahertz. But for simplifications, we assumed in this phase this one. And we wanted to use just one 5G private network as interferer, just to make it simple. And even that proves very difficult. So we started to cooperate with the BDG, the large users of telecom equipment, telecom users. We sought cooperation with equipment providers because you also need a 5G private network to work with. And we discussed within a group several 5G use cases. And of course, we have two main frequency users in the Netherlands, Schiphol and Rotterdam Port. And we discussed use cases which they had, which would like to test with 5G. Unfortunately, at Schiphol, and I'm not sure if the slides are in correct order, they are, altimeters on board of planes of helicopters working in the 4.4 gigahertz, which is very close to the band we want to pilot. And as a precaution, we decided not to use a 5G network in this frequency band at Schiphol until more is known about compatibility between 5G and the altimeters, because well, it would be very handy if altimeters give the wrong height because of 5G network.
Detail. Pilots need special license. Then
Yeah.
Don't see them.
Yeah. Okay. Yeah. It's 0. Yeah. Yeah. The radar always gives the height above ground, even if it's turbulent. So that's one of the topics which has to be studied further. So we for now stopped with the pilot at Schiphol. And you might have seen we continued with the Rotterdam Port use case. And this afternoon we had a meeting at the ECT terminal to find a site for the 5G network. So we're really making steps with that. Part of the pilot is the fact that we can sense interference at the satellite reception site. And since satellite reception is very sensitive, the sensing of possible interference from a 5G base station also has to be very sensitive, which does require some smart engineering from colleagues of mine, having a smart antenna, low noise amplifiers, short cables, and a very sensitive reception protocol. So that's a challenge. Maybe in future you could use information from the satellite dishes themselves, from the satellite operator themselves, which obviously also sees interference. So that could be another signal. Yeah. Yeah. Yeah, definitely. Yeah, that's one of the refinements. We had to make a lot of simplification to get it running. That's correct. Yeah.
Would you mind to repeat the comment
I'm
for
sorry.
the?
there was a remark that the best way to sense interference was from directly from the IQ output of the dishes or the receiver straight after the dishes. Then you're actually measuring what's happening in real life, and not a secondary sensing system, which also can be a filter. But that's correct. Yeah.
Thank you.
One of the other remarks, because when there is interference, for instance, in case of ducting, the 5G private network has to reduce power, or even worst case, has to switch off. That means that frequency band is not 100% of time available for a use case. And that's very difficult for users to accept and to deal with. That means, well, if I have I use it for my operation, and I lose that frequency, what can I do with the operation? So I need an alternative to keep communicating. They call it an anchor band or alternative channel, or which can be a nice mix between, for instance, a private network and a public network. So when your private network has to shut down because of interference, you can fall back on the private network. Part of the concept is the reduction of output power of a 5G base station. We thought, well, that's quite easily just send some command and it will reduce power. That doesn't seem to be that easy if you look at the equipment providers. What I didn't mention in my presentation, I thought, oh, it's what we call dynamic frequency management. We're not talking about millisecond scale, but ducting can happen quite quickly within minutes. So we're thinking about this system has to regulate power within, let's say, 20 seconds, 30 seconds, quite fast. And it seems that base stations, which are used nowadays for 5G, also for private 5G networks, cannot adjust power seamlessly. So you can request them to change power. They have to unlock or lock one way, unlock all the devices connected to the base station. They can switch off. They can set a new power, and they can switch on again, and then all devices can connect again. It takes at least 2 minutes if you do it fast. But there are a lot of challenges. It makes the use case a lot more difficult. So that's definitely one we have to work on. And of course, get a location for antennas, find space for your sensing equipment is always a challenge. And of course, there has to be some mechanism. For this phase of the pilot, it can be very simple because it's just one receiver and one base station we have to control. But of course, there has to be something which makes the decisions for you and do measurements. And it has to be built. It's not always easy. It's not difficult, but it's not always easy to get it done. Goal of the pilot. Almost there. Yeah. Get it to work technically. That seems to be a big challenge. So that's one of the goals, just to have a little bit of proof of concept of some elements of dynamic spectrum sharing. What we also want to learn is how does the use case behave? So if the customer of the 5G private network has a use case, how does it deal when the power of the 5G base station reduces or it even switches off? How does it influence his use case, and has he ways to handle that in different ways? Of course, gather measurements, analyze data. And one of the other things, and I think you have to build trust about, especially the incumbent user, which feels vulnerable. He always has protected spectrum, and now we're going to place transmitters in his neighborhood, and the system has to protect him. So it's building trust. It's very important. So we hope this will work. And of course, some things we're thinking of for the future. I already mentioned in this pilot we're using one 5G private base station. how nice would it be that everyone who wants to use this frequency band for 5G can just ask the system for frequency space. So there has to be some system granting access to the spectrum for the 5G networks. I already mentioned we modeled the different dishes of the satellite ground station as one dish to protect. Of course, you can have some refinement if you know the actual dishes and the frequency they use and the direction they're pointing. You can get much more frequency space available. Because of simplification, you just assume worst case. One other interesting thing we found out, at the moment we're sensing with an external system, which has an antenna looking towards the interferer. If we think the concept through, you could have more 5G base stations in that area. So if we measure interference, which base station has to reduce power? We don't know. It's all the base stations in that direction. So there could be any refinement to reduce the size of the sensing system. Say, well, it's only the base station in that direction. So the other ones can keep transmitting. Otherwise, you might say to 100 base stations, just reduce your power because we don't know who is causing interference, but some of you is causing interference. So that might be an enhancement. And one thing my colleagues are currently looking into is the possibilities to have some fingerprinting of the 5G base stations. If you recognize the actual base station which is causing interference, then you only ask that base station to reduce power. But that means that you have to fingerprint the 5G signal and correlate it to one user, which is, as far as I understand, quite challenging. One other thing we think of can be an enhancement is in the current pilot, we asked the base station to reduce power in all directions, just reduce transmitter power. Of course, there are more smart antennas. If we just give the command, okay, stop interfering in our direction, more enhanced antennas could just apply nulling in our direction, so they can keep transmitting in the other directions. A more, refined solution, of course. Standardizing. Now we have to deal with protocols, specific protocols from the vendors to talk with the base station. We figured out a protocol for ourselves to talk between our measurement system and the controlling system. Of course, if you want to use this large scale, you have to have more standards. AI might be a possibility. We have to train it very well, but it might be a possibility for our control system. And I think I'm reaching my last slide. Goal at the moment for the pilot is get the technique to work. It will be very interesting what policies we can apply to whatever the system will be doing. So that's another thought. I think that's specifically for policymakers. How to deal if there are more requests for spectrum. Do you include pricing, for instance? Fair use, whatever. All kinds of policies which has to be implemented in the system in a later phase. Who will manage the system? Should it be distributed? Should it be by governments? European-wide? I don't know. And one of the issues, of course, to address how to deal with cross-border interference. If you're going for systems like this in a European scale, of course you will get cross-border issues. That means that systems have to talk to each other cross-border, which does sound simple, but in practice you have to arrange a lot. So the pilot, this is my final slide, are really tiny steps towards the ideal spectrum sharing described, but at least I think we're making steps. Thank you.
Any questions? Yeah, Jaap?
We cannot hear.
Yeah, I will repeat.
Oh, thank you.
Yeah, yeah, was ready. The general question is, can we use an array of receivers to filter out any noise or unwanted signals? Yeah. For instance, LoFar. Yeah, I think we can. But I think the ideal situation in this case, and I have to agree, it's receiver centric. So if you really want to know what a receiver sees no interference, you have to look at the receiver. But it's not relevant if a satellite station 100 kilometers away does receive something. I'm curious about protection my station, and especially when looking at ducting. Yeah, but it doesn't give you more information, because I still need to know how to protect my station, and that's yeah. 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 Yeah, I've agreed that do we copy or reinvent the wheel if you're looking to CBRS? In part we are. Of course, we looked into CBRS, and it's I think for using in pilots much too complicated. And one of the issues at the moment in Europe is our policy is not that strong. How to say? It's not really enforcing models like the CBRS. So we decided to go from bottom up to see what's possible. And of course, we want to use or copy elements from CBRS. But we cannot do it as Netherlands alone. So yeah, it's very nice what's happening over there, but we're looking into it and we're using what we can and do what we can bottom up at the moment.
There's one more question, but I'm going to give the people online also a chance, and then I come to Sonia. Is a question of the online?
Yes, I would like to ask Mr. Rogier Noldus. He has 2 questions pending. Would it be okay to unmute? Yeah.
Yes, thanks, Sonia. Okay, well, indeed, I've got two questions. First of all, the fingerprinting concept is extremely interesting, and you do trigger me to look into that to see how we could potentially resolve that. But how is ducting detected today, considering the fact that so far as I understand, the effect of ducting occurs over a long distance away from the base station? So, I mean, yeah, can you explain how can you detect that ducting is occurring?
By measuring, that's the basic principle. It's not happening close to the base station. So yeah, it's happening a long distance. So the only thing you can do is measure at that distance, and in our case, at the receiver to protect. The measurements my colleagues did for 1 or 2 years was basically set up having a beacon transmitter on one side of the Netherlands, or actually at 4 locations, and a receiver at the other side, and just measure. And of course, then you see the graph I showed in the.
Yeah. Okay. I see. So you're actually injecting radio transmission, which and you're checking whether ducting occurs. But if you're just receiving, say, noise, you're receiving interference, how could you know that this interference actually constitutes ducting or is caused by ducting if you're not actively generating the ducting?
That's a very good one. We detecting it assuming there are no other unknown transmitters. That's one. So yeah, you got me there.
Okay.
Yeah, that's the only way it works.
Okay, understood. I mean, it's very new, this probably, and I assume that there's still further research needed to detect it, like this fingerprinting technique.
Yeah, and well, I did mention it in the presentation. for our own purposes, we place a beacon transmitter also next to
Yeah.
the 5G base station, just to have extra measurements. So yeah.
Okay, no, that's fine. I mean, understood. There's still work ongoing. Last question, then I'll keep it short. Okay, so from the slides where you introduced the ducting concept, we see that the ducting occurs by the radio signal which is transmitted in upwards direction, and it goes towards a particular layer of the ether where the actual ducting in horizontal direction is occurring. One logical thought is that, well, in order to prevent the ducting from occurring is preventing this radio signal from being transmitted in upwards direction.
Okay.
And make sure that from the base station, it's only transmitted in horizontal direction or even towards the ground, which is where it is needed.
You're a good viewer. Yeah, it's one of the pictures I used from a colleague. Based on the research, it doesn't matter if you direct upwards or horizontally in this case. The phenomenon, the pilot transmitters used during the tests just pointed horizontally, and it appears that somehow you get into the duct. It doesn't. You don't have to point upwards to get in the duct.
Yeah. Okay.
I think I have to agree that if you point downwards a lot, you can prohibit ducting to occur.
Understood. Yeah, it's understood. I mean, it's these side lobes that occur in the radio antenna.
Yeah, I'm not sure that was the case, but then we have.
Okay.
I think the study is mentioned in the papers, and it might be interesting to look into that.
Yeah. Okay. Good. Thanks. Thank you.
Thank you for the question. There's another one here.
Maybe I can add something that if you point at the horizon, when the radio wave reaches the horizon, at that point it's horizontal already.
So the Earth is round, right, and not.
Oh. Yeah, I mentioned four.
You mentioned four.
No, code is one of
Can
the.
you repeat the question?
So the question was, I mentioned three degrees to 3 ways to share, the separation ways to share frequency space. There were 4 in the paper, and it's now called signal separation. In earlier versions of the recommendation, it was used code separation, which there were only mentioned 2, which was CDMA and polarization diversity. Something. That's the only 2 they mentioned, and there was a lot of debate about is that there's more than only code. So they mentioned it signal separation, which now includes reduction of interfering power also.
Yeah, I have another question.
We experienced years ago kind of ducting phenomenon. Was in certain times there was a signal all over the Netherlands, the 3.5 gigahertz band. Turns out it was a visiting Navy ship with the Americans. We had this radar. So we went to the American ambassador and asked, can they switch their radar off? Yeah. The ambassador said no. But says no power on the net. So we went to the Navy and they said no, there can be incoming phones everywhere in the world where we haven't been the radar on.
I'm not sure we're going to solve that with dynamic spectrum management in Europe, but it might be that the CBS system is coping with that.
But it's not periodic. It's not periodic. Yeah, well, the radar is periodic. Yeah, maybe something.
It probably is, yes. Yeah.
Could you briefly summarize the question in the end?
I'm not sure it was a question, yeah, but it was about
the comment.
The comment was about American Navy using 3.5 gigahertz radar of a ship causing interference, possibly.
Yeah. I didn't.
Okay.
Didn't want it. Holland signaal. Okay. Are there more online questions?
No, there are no.
Okay. Here in the room, more questions? No? Oh, yes, one.
En je ziet er binnen de inhoud. Very short. At all, that been relevant pilot, or there might possibly have been.
As far as I have to believe my colleagues doing measurements, they said, well, it's enough distance to have that thing.
It's like,
Yeah, it's 60 something. Yeah.
Okay. Thank you all, the people here, the people online, and in particular the two speakers. I would like an extra applause. KIVI Telecom seminars, the chairman of KIVI Telecom comes here and you. However, the KIVI Telecom.
Close to the microphone, Ines.
I didn't want this to be broadcast, but
Sorry.
no, I was saying that KIVI Telecom normally presents people a little something to express our appreciation. And this has happened online. So if you open your mailbox, PBS and Frank, then there should be something. So check the spam folder. Yeah. Okay.
There is a question from one of the participants, Mr. Rogier Noldus, has raised the hand.
Oh, sorry. I raised my mistake. I was trying to
Oh.
applaud. So by mistake, I raised my hand.
Okay.
Thanks anyway.
Okay. So we will now, okay, there is a few drinks outside and some other stuff. So thanks again, everybody.